Hi guys, welcome back to AP Calculus. We're still working with sequence and series, particularly series and how they, or when they converge and when they don't converge. So we're going to look at alternating series today, and we're going to look at something called absolute convergence versus conditional convergence. All right, so alternating series. I just want to warn you, this is not necessarily on the AP exam, but it is stuff that kind of gets covered. Like the alternating series test by itself is not necessarily on there, but there are such things as alternating series. And an alternating series it switches signs. So like it has like either a -1 to the n as part of it, and then some other stuff with n, or -1 to the n plus 1, or n minus 1 also works out the same way. So like one term will be positive, the next term will be negative, and then positive, and then negative, and then positive, and negative, and so on. So it alternates between positive and negative. All right, to tell if it converges, we have two conditions. The first is the limit has to go to 0. The second is that the series has to be, if we take out the negative sign that is, the series has to be decreasing. Right? So if we check those two conditions and those work out, then it converges. If either one of those fails, then it diverges. So we can take a look at the first one here. We could actually do this with geometric right here, where r would be, the -1/2. So the absolute value of r would be 1/2, which is less than 1. So we know that this should converge, but let's try and do this with alternating series. So we'll just kind of leave this off to the side here. So if we treated this as an alternating series, we could put the negative on top. It'd be -1 to the n over 2 to the n. So we leave out the -1 part, and we're really just looking at, so our a sub n here is 1 over 2 to the n. And now we want to know, does this limit go to 0? Limit as n goes to infinity of 1 over 2 to the n. Well, yeah, that definitely does go to 0. And is it decreasing? So is 1 over 2 to the n greater than 1 over 2 to the n plus 1? Well, this is 1 over 2 to the times 2 to the n, like that. So this is really half of 1 over 2 to the n. So yeah, it's decreasing. All right, so this is definitely less than what it was here. It's half of what it was there. So both of these conditions check out. So that tells us that this guy, the original guy, does converge by the alternating series test. So we just confirmed it. All right, next one. So again, we kind of look at this as the -1 to the n plus 1 times, say, 1 over n. So this is like our a sub n right here. So we look at the limit as n goes to infinity of 1 over n. And sure enough, that does equal 0. And then is it decreasing? Is 1 over n greater than 1 over n plus 1? Yeah, it is. This bottom's bigger, so it's decreasing. So both of these check out. So this series does converge. So it converges. All right, which is odd, because if we take out the negative there, we know that that's the harmonic series. Just 1 over n by itself diverges. So this -1 does a lot of work for us there. It helps it go down to 0. All right, so this guy, well, we've got a negative in here. We could kind of pull that out and say it's like -1 to the n minus 1 times n over 2 to the n minus 1, like that. And now we can look at this guy and say, okay, well, what happens with the limit? So this is our a sub n right here. And this is our -1 part. So we take the limit as n goes to infinity of n over 2 to the n minus 1. If you need to do L'Hopital's rule here, you can, but the exponential is always going to be bigger than just the n. So it's going to go to 0. That checks out. And we want to look, is n plus 1 over 2 to the n minus 1, is that greater than n? Oops, did it backwards. N, there we go. N plus 1 over 2 to the n minus 1 plus 1, so just 2 to the n. All right, so this is basically half of n plus 1 over 2 to the n minus 1. So the n and the 2 to the n, they don't make a big difference on top. Like, it's getting a little bit bigger, but it's half of what it is on the bottom. Like, so the whole thing is half of what it was before with just that plus 1 on top. That is going to check out. Both of these conditions work. So this does converge. All right, and the last one here. So again, we pull out this n, or this -1 part, and we are left with our a sub n is n plus 1 over n. So if we look at the limit as n goes to infinity of n plus 1 over n, well, that equals 1. All right, we can just look at the highest term on each one. It's going to go to 1, which is not 0. All right, so this guy does not converge. He diverges. We don't even have to check the other part. We just know. All right, so some other things about alternating series. So when you keep adding a term and then subtracting a term and then adding a term and then subtracting the term, if we want to know what the sum is, like the actual sum, if we stop at any point, the difference between the actual sum and the partial sum, or what we call the remainder, is just the next term. All right, so the next term is telling us what's the difference between, what's the biggest possible difference between the actual sum and the partial sum is always just whatever the next term is. So how many terms would be needed to approximate the sum of the series -1 to the n plus 1 over 1 over n factorial to 3 decimal places? So that'd be 0.001. We want to be correct in our sum. All right, well, we could take a look at this. Like if we plug in 1, let's see, we'll get -1 squared, and we'll have 1 over 1 factorial, which is just 1 for our first term. Our second term, we plug in 2. We're going to get -1 over 2 factorial. All right, our next term, if we plug in 3, we're going to go back to positive, and we're going to get 3 factorial, which is 6, and then negative, and then 4 factorial, which is 24, and then positive, and then 5 factorial, which is 120, and then negative, and then positive, and so on. So if we just start adding up terms, we get 1. If we add those two up, we get 1/2. If we add a 6 to that, let's see, that's 3 6 plus 1 6, that's 4 6, or 2/3. We subtract 1/24 from that. So this would be, what, 16/24 minus 1/24 would be 15/24, and so on. I'm not going to try and do the next one in my head. All right, but it is just getting closer and closer to some actual value, right? Because this is going to converge by the alternating series test. All right, and the difference between each series is just the next term between the sum, the partial sum. Is this the next term? So we're going to subtract something and then add something and then subtract something smaller, then add something even smaller. So we want to know, when does a term get smaller than that? So when is 1 over n factorial less than or equal to 0.001? All right, well, we can multiply this up and divide this down. So 1 over 0.001 is less than or equal to n factorial. This is 1,000. So when is n factorial greater than 1,000? So this was 5 factorial. 6 factorial is 720. 7 factorial gets really big. So I worked them out ahead of time. And of course, my calculator has turned off since then. But there we are. 7 factorial is 5,000. So when n equals 7. So if we get to 7 terms, we've got it to 3 decimal places. All right, so that's kind of a neat thing. The next one, let's just try and approximate the sum of the series using the first 5 terms, which is actually kind of what we did. We did the first 4 up here. But we want the sum of this one. So our first term, we're just going to plug in. We start at 1. So if we plug in 1, 1 minus 1 is 0. So -1 to the 0 is 1. We plug in 1 on the bottom, we get 1. Plus the next term, if we plug in 2, we're going to get -1 over 2 plus 1 over 3 minus 1 over 4, because I know it's going to be negative, plus 1 over 5. And then we just got to add those up, or add and subtract those up, I guess you could say. So we've got 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. And we get that that is 0.78333. All right, but that's not really going to an answer very quickly, because this is only 1/5, which is what, 0.2? So I mean, that could be off by as much as our next term is 1/6, which is 0.1666 repeating. So it could be off by as much as 0.16. Right? So it's going to be somewhere between 1/2 and 1, but we're not really sure what it is off the top of our heads here. All right, absolute convergence. All right, so we say something converges absolutely if we get rid of the negative, like we take the absolute value of it and it still converges. Then the original guy converged absolutely. All right, but if we get rid of the absolute value and it diverges, then we say it converges conditionally. All right, so here's an example. We have -1 to the n plus 1 over n. All right, we know from alternating series that this would converge. All right, but if we get rid of the -1, if we look at just the sum of just 1 over n, that diverges. And this original guy converges. All right, so if we take the absolute value and it diverges, but the original guy converges, this guy converges conditionally. All right, let's take a look at the next one here. All right, so if we look at this guy, this is just like we had before, but we had 2 on the bottom before. So this guy converges. Alternating series will get us that, or the ratio, or not ratio, but the radius would be 1/3 here. The absolute value of the radius would be 1/3, so it would be a geometric that converges. But if we get rid of the -1 on top, and we look at this as 1 over 3 to the n, or 1/3 to the n, this also still converges. All right, it's r is 1/3, which is less than 1. It's geometric, so it converges. So they both converge. So this guy, we say, converges absolutely. There we go. And the last one here, I guess we'll go over this way with it. So if we look at this guy as it is now, we could use just maybe a comparison test, because sine of n is going to flip around to all sorts of weird things when we plug in whole numbers in here. Like if we had a pi there, maybe that'd be some difference. But at 1, at 2, at 3, some of it's going to be positive, some of it's going to be negative. But I do know something about sine. It's always less than or equal to 1. So we could just do a comparison test here to 1 over n squared. It's definitely less than that. And 1 over n squared, this converges by p series. So that checks out. But if we look at the absolute value of this guy, so that'd just be the absolute value of sine of n over n squared, is also still less than or equal to 1 over n squared. It might be a little bit bigger than this guy sometimes, because so the negative terms are going to turn positive, but it's still going to be less than this. So by the comparison test, this still converges, because this is another p series, where p equals 2, it's just greater than 1. All right, so both of them converge, so this means this guy converges absolutely. All right. All right, so that's alternating series and absolute and conditional convergence. The next video we're going to go over, I believe, one of our last tests. It's a cool one though.